Hello Chem 1A, this is Chapter 12, Lecture Video 4, and we're going to be talking about how those intermolecular forces we've been talking about can affect our properties of liquids, starting with vapor pressure. So liquids always have some of their substance in the gaseous state above the liquid, right? So if we have like a glass of pure water, there is some water in the gaseous state above that liquid in the glass. In an open container, the liquid will continually evaporate even if we're below the boiling point. So kind of think about if you've ever spilled a drop of water on a table or something, and then maybe 30 minutes later you come back and the drop of water is gone. Nobody wiped it up. It just evaporated. We're still below the boiling point in your house, hopefully. And so why did it evaporate? It evaporated due to it going into the gaseous state. In a sealed container, however, that liquid will evaporate and it'll start to build up in the container, right? So if the container is sealed, the vapor doesn't escape. So it starts to build up. And eventually the liquid and the gaseous state substance, right, will eventually reach what we call equilibrium, where we have equal rates of evaporation and condensation occurring. So at the same rate that our liquid is evaporating, it's also condensing. And so we have this constant amount of gaseous pressure of the pure substance in the gaseous state above the liquid. Now, vapor pressure will increase with temperature. So as we increase the temperature of our liquid, the vapor pressure will rise. Now, let's talk about how vapor pressure is affected by intermolecular forces. Basically, higher intermolecular force strength will result in a lower vapor pressure. And if you think about the reason why this occurs, it hopefully makes some sense. In order for our liquid molecules to go into the gaseous state, the intermolecular forces holding the liquid molecules together have to be broken. The stronger they are, the less likely those molecules will break apart and evaporate into the gaseous state. So the stronger your intermolecular force strength, the lower your vapor pressure of your liquid will be. So let's look at vapor pressure and temperature a little bit more in depth. We have what's known as the Clausius-Clapeyron equation. And this equation here, we can kind of think of these as vapor pressures, but I just have them labeled as P1 and P2. Allows us to calculate what the vapor pressure will be at one temperature if we know it at another temperature, and we know the delta H of vaporization, or the heat of vaporization. Or really, we can calculate any one value in this equation other than R if we know all the other values. The R value in this equation is different from what we're used to. It's 8.314, and the difference is really just a unit difference. Like the 0.08206 R value, that has different units here, and that's why they're different values. But we have to use these units for this equation, so we have to use this numeric value. So let's do a problem, right? If water has a vapor pressure of 17.5 torr at 20 degrees Celsius, what is the vapor pressure of water at 75 degrees Celsius? The delta H for water is 40.7 kilojoules per mole. So if we set up our problem, we have the natural log, and we have our vapor pressure 1 or 2. It doesn't really matter which one you define as what, but since we're calculating the vapor pressure, I'm going to put vapor pressure 2 as my unknown and put 17.5 here in my denominator. I'm going to set this equal to delta H, which we are given, 40.7 kilojoules per mole, over R, which is 8.314 joules over moles Kelvin. Now, this joules thing can get us into some trouble because this value down here is in kilojoules. So I need to convert that so that they cancel. And then I'm going to do 1 over my T1, which is the 20 degrees Celsius one. So that's 293 Kelvin minus 1 over T2, which is my 75 degrees Celsius value. So we got to convert that to Kelvin. 75 plus 273.15 gives me 348
and then we subtract, right? Now, so this is our situation. I'm going to calculate all of this to start on the right here, and I'll get that the natural log of P2 over 17.5 is equal to 2.641. Now I need to get rid of this natural log, and the way we do that is we take the e of both sides. This cancels this down to P2 over 17.5 is equal to 14.03. And now I can just multiply both sides, and P2 is going to be equal to 245 torr. So pressure units in this equation don't matter as long as you stay consistent between P1 and P2, but temperature must be in Kelvin. Delta HVAP, usually given in kilojoules, should probably be in joules. Otherwise, I give you this equation on the test. You don't need to memorize it. All right, so let's talk about boiling points. Boiling points are defined as the temperature at which something happens. Now, most people that aren't really quite certain of the definition of a boiling point might say that it's the temperature at which a liquid turns into a gas. And that is not actually the definition of a boiling point, because like I said earlier, if we just leave a glass of water out at room temperature, the liquid will turn into a gas, just very slowly, not very much of it, but it'll happen. So that's not really the correct definition of what a boiling point is. It's defined as the temperature at which the vapor pressure of our liquid is equal to external pressure. Now, if we're at sea level, that means our external pressure is 1 atm. Now, when you see the word normal in front of boiling point, that means that your external pressure is defined as 1 atm. So whenever we say, hey, the boiling point of water is 100 degrees Celsius, that's the normal boiling point of water. Boiling points of liquids change with external pressure. So if you're boiling your water at sea level, then yeah, the boiling point's 100 degrees Celsius for water. But if you're at the top of a mountain, it's probably going to be significantly lower than that, because as we go up in altitude, the pressure decreases. Boiling points are affected by intermolecular forces as well. So the stronger your intermolecular forces, the higher your boiling point will be. And this is just kind of an example of that elevation thing, right? So if you're boiling at sea level, yeah, hey, guess what? Your boiling point for water is probably around 100 degrees Celsius. If you're in Denver, the mile-high city, it's only 95. And for some reason, if you don't have anything better to do on the top of Everest than boiling water, the boiling point will be 76.5 degrees Celsius. I highly doubt that would be the case, but whatever. All right, finally, viscosity. If you don't know anything about viscosity, I always like to use syrup as my example because I probably will have diabetes someday. I eat way too many sweets, and I love syrup. It's defined as the relative ease with which individual molecules of liquid will move past each other or with respect to each other. Now, if you think about syrup, different types of syrups have different types of viscosity. Now, if you are drinking if you're eating syrup that's like Aunt Jemima or like random just generic brand syrup off the shelf, it probably has a really thick, slow flow, right? Like if you turn it upside down, it flows very slowly. Whereas if you got something like the delicious maple syrup, if you're eating 100% maple syrup, those of you that have used it know that it flows much quicker. The viscosity is much lower for maple syrup than regular syrup. But things that move very slowly have a high viscosity when we pour them. The stronger your intermolecular forces, the more viscous your substance will be. So something like honey or syrup, these are very viscous liquids. They do not flow very fast. What that tells us about them is that they have very strong intermolecular forces present within those systems. If you've ever cooked with honey or syrup, though, you might know that they become very, they move around just almost like water does. The viscosity decreases significantly as we increase temperature because we start breaking those intermolecular forces with the increased energy due to the temperature change. And that makes the molecules start to move around faster past each other and stuff. So our viscosity decreases as we increase temperature. And you should know both these trends. All right. So we're going to talk about one last thing that changes with intermolecular force strength, and that is critical temperature and pressure. Critical temperature and pressure are defined as the highest temperature and pressure that a substance can exist as a liquid. So water can be a liquid above 100 degrees Celsius, just not at 1 atm of pressure. But if I increase pressure, the temperature that my boiling point is will also increase, therefore increasing the temperature at which my water can remain a liquid. But there's a limit to that. I can increase pressure, and at some point I get to this point known as the critical point, where even if I increase pressure after that temperature, the water's in the gaseous state. And this is known as the critical temperature and pressure, or the critical point. So these two, right, together, these together are called the critical point. As we increase intermolecular forces, we have a higher critical temperature and a higher critical point in general. So the stronger our intermolecular forces within the molecule, the higher our critical point will be. So just to kind of summarize everything that we just covered, things with strong intermolecular forces will have low vapor pressures, low rates of evaporation because of that low vapor pressure, a high boiling point, are more viscous, and have high critical temperatures. And the rest of this slide is pretty much exactly the opposite of that. So weak intermolecular force molecules are going to have higher vapor pressure. High rates of evaporation, which we'll talk about more, is called volatile. Like gasoline's really volatile. If you've ever spilled it on the side of the car when at the pump, it evaporates like that. They have low boiling points, and they are less viscous, and finally they have lower critical temperatures. So this kind of gives us some trends to kind of help us figure some stuff out. Like if I could ask you to put the following molecules based on their intermolecular forces in order of increasing or decreasing, I don't know, vapor pressure or boiling point or viscosity or critical temperature. So you should be able to use these trends to kind of match what we learned in the last video to these properties.